Hi everyone, welcome to Princeton Theory Lunch. Today we are very happy to invite Professor Qiao from University of Technology at Sydney, and he's now visiting scholar in field for advanced study hosted by Abby Wickerson, and previously he obtained his PhD in Qiao University under the supervised by Professor Andy Yao and Lassie Papai, and his research interest is focusing computational complexity and algebraic computation. And today he's giving a talk on tensor isomorphism, complexity algorithms.
Yeah, thanks so much, Zhongtian, and thank you all for coming. So actually, I was at this theory launch maybe 15 years ago. So it's great to be here, to come back and to speak at this seminar series. I'm Youming, and you can see I come from Sydney, and luckily I have been around for some time, so I didn't need to fly for 20 hours from Sydney to Newark or something. Today, I would like to talk about tensor isomorphism, basically covering the three aspects: complexity and algorithms and cryptography. Hopefully, there will be some aspect you will find more interesting. And if you have any question, please just stop me. So the outline is as follows. So first, I will introduce the so-called isomorphism problems, starting from graphs and matrices. Then we go to tensors. And after introducing tensor isomorphism, we will talk about the three aspects: complexity. We're basically here for complexity aspect. The message here is that tensor isomorphism can serve as some unifying isomorphism problems for some algebraic structures. Then we go to algorithms. There has been some pretty exciting progress in the past few years on tensor isomorphism, group isomorphism, and so though the progress is pretty exciting, but the algorithms are still exponential. So meaning that they are actually still hard algorithmic problems. And based on this algorithmic hardness, then we go to the cryptography side, because once we have some hard problem, hopefully we can use it in crypto. And this is indeed the case for tensor isomorphism. So finally, I'll conclude and pose some open problems. This is based on to work with many collaborators, and I would like to emphasize that Josh Groucho and Gabriel Ivanush are really long-time collaborators. And this work cannot be done without these wonderful collaborators. So yeah, we'll get started. Talk about isomorphisms, problems going from graphs and matrices to tensors. So what are isomorphism problems? Isomorphism problems basically are saying that we are given two mathematical structures. For us, usually the structures will be combinatorial structures or algebraic structures, and we want to know whether they are essentially the same. The most famous example will be, of course, graph isomorphism. That is, we are given two graphs. We want to know whether these two graphs are the same up to relabeling the vertices. For example, we have a 5-cycle graph and a 5-star graph, and they look different, right? But on the other hand, you can easily see that by relabeling the vertices, like this, 1, 2, 3, 4, 5, 1, then the star graph becomes the cycle graph. So these two graphs are essentially the same, just we are labeling the vertices somehow differently. Just to refresh your mind, basically. So it's one of the earliest problems considered in the framework called P and NP. And actually, both Cook and Levin, when they were defining NP completeness, they have graph ISO in their minds. And also, it's a motivated permutation group algorithms by Papai and Lux. And also, it serves as a classical example for interactive protocols, zero knowledge. So it's a very intriguing problem from the theory of computing viewpoint. Then another problem is the so-called matrix equivalence problem. It's so basic that we kind of don't really talk about it much. But we can formulate the matrix equivalence problem as, suppose we are given two matrices A and B. We want to know whether A and B are the same by basically row operations and column operations, or in other words, multiplied by invertible matrices L on the right and R on the left, L on the left and R on the right. For example, suppose we are given these two 2x2 matrices, and you want to know whether they are essentially the same or not. And in this case, it's easy. You can find this invertible matrix L, invertible matrix R, such that A equals L E R. And if you think about it a little bit, you will realize that this is an easy problem, because from basic linear algebra, we know that two matrices are equivalent if and only if their ranks are the same. So you can also bring it to canonical form and so on. So that's the easy problem in general. On the other hand, there are also two related notions called matrix similarity, where A and B are square matrices, R equals L inverse, as well as matrix congruence, namely R should be equal to L transpose. They are also both important linear topics in linear algebra. So that's matrix equivalence. On the other hand, we want to go beyond these examples and want to talk about tensors. So the main object of interest of this talk will be tensors or multi-way arrays. To start with, we know that matrices are two-way arrays, right? So for example, this is a 2x2 matrix. And usually for this talk, we will sometimes draw a matrix as a square. So it's a square of numbers. Then we go to three-way arrays, right? For three-way arrays, we will see it as basically a cube of numbers. So I draw a cube, but it's not a solid cube. But basically, you see this if it's a 2x2x2 cube, then you have the frontal slice being this matrix, and then you have the back slice being this matrix. So it's when I draw a cube, it's not a solid cube; it's a cube of numbers. So they are the three-way arrays. If we don't want to draw the three-dimensional object, we will present it as, for example, a matrix tuple, a tuple of matrices by slicing this cube along some direction. So that's a three-way arrays. And remember, also we talked about matrix equivalence is defined by two matrices being the same up to left multiplying L and right multiplying R, invertible matrices. So, and what are these L and R doing? So L is basically doing linear combinations of the rows, right? And R is doing the linear combinations of the columns. Then for three-way arrays, now because we have three directions, so naturally we could have three invertible matrices L acting on the left, R acting on the right, and the T acting on the third direction. So what L is doing is basically doing linear combinations on the horizontal slices. R is doing linear combinations on the vertical slices, and the T is doing linear combination along the third direction. So this is quite natural so far, just generalizing from two-way arrays to three-way arrays. Now, of course, we can define tensor isomorphism, right? Tensor isomorphism basically asks, given these two cubes of numbers, we want to know whether these two cubes of numbers are the same up to L, invertible matrices L, R, and T, doing linear combinations on the three sides. And if you want to write it formally, you can write it as a matrix tuple, and say they are n by n matrices. You want to know whether there exists three invertible matrices L, R, T, such that every slice equals L multiplied on the left, R multiplied on the right, and T doing the linear combinations along the third direction. But this is not, basically, I guess from this picture, you would know what this problem is. Okay, so far, so good. So this is our tensor isomorphism problem. So I want to mention some basic facts and relations of tensor isomorphism problem with some why it's interesting, where does it appear. So tensor isomorphism appears naturally in coding theory when we talk about the so-called matrix codes, because matrix codes are linear spaces of matrices, and then you want to know whether two matrix codes are equivalent. Essentially, this is tensor isomorphism. And it also appears naturally in quantum information in the notion so-called stochastic local operation and classical communication between pure quantum states. And the complexity of tensor isomorphism would actually depend on the underlying field. So if it's a finite field, then it will be, as graph ISO, it will be in NP intersect co-AM. The co-AM essentially because you can do some interactive protocols, but just as like the co-AM protocol for graph ISO. On the other hand, over complex number field, we only know that it's in AM, assuming generalized Riemann hypothesis. This is because you can express solving tensor ISO as solving polynomial equations. Namely, you assume that your LRT, you are matrix of variables, and then you can easily write, cubic polynomials, and the solvability of these cubic polynomials will give you the solution of tensor ISO. Then you can use the so-called Nuss-Dahlen sets in AM to put tensor ISO over complex number to be in AM. But on the other hand, here's an open question. That is, we don't know whether tensor isomorphism over complex number is in AM intersect co-AM or not, because usually for this isomorphism type question, they don't seem quite like NP hard usually. So here is an open question, namely we don't really know the tensor isomorphism complexity status of tensor iso over complex number. Yeah. Right, that's in, well, the matrix is maybe, bit length. Over complex number, there will be bit length issue. Right, you don't know how much you can control the bit length as well. Oh, for this AM or for this AM, I think it's the Turing machine model. This is basically this Pascal Corin's result about loose balance as easy. Right, exactly. I don't. Mm-hmm. Mm-hmm. For tensor S over complex number or in general? We will talk about this later. Okay, so there will be algorithm part. You will see what we know about algorithm. Okay, so that's basic complexity status of tensor ISO. And then there's also, relating tensor ISO with graph ISO and so-called code equivalence. So there are another classical isomorphism problem called code equivalence, which basically asks if you are given two linear codes or two linear spaces, you want to know whether these two linear spaces are the same after permuting the coordinates. So this is a code equivalence. It has been studied in coding theory since 1980s. And we basically have this relation, namely graph ISO reduces to code equivalence, and code equivalence reduces to tensor ISO. So that's, the relation of tensor ISO with respect to some other classical isomorphism. Okay, so this is, the basic, to tell you about what the tensor isomorph problem is and its basic complexity and status. Now we are going to talk about the complexity side, and the main message here is that tensor ISO could serve as a unifying problem for several algebraic structures. Because we want to talk about complexity, we introduce the so-called tensor isomorphism complexity class. So the definition is easy, right? It just consists of all the problems that are polynomial time reducible to the tensor ISO problem. And this is not so strange because you probably have heard of this graph ISO complexity class, which consists of problems polynomial time reducible to graph ISO. And there's a monograph regarding this graph ISO complexity and so on. So far we have been working on this tensor ISO complexity class with my collaborator Josh, and we have a series of 5 papers, and it's motivated by complexity considerations, and it leads to several interesting and unexpected connections. I'll give a very quick, it's 5 papers, so definitely I cannot cover all of them in this talk. So in the first paper, this is the message from the first paper. It seems that tensor ISO captures isomorphism problem for many algebraic structures. And then we look at some variations of the theme, namely when tensor ISO is acted by different types of groups, such as from general linear group to orthogonal unitary or symplectic groups, what would happen? And also, if you change from general linear group over a field to general linear group over a commutative ring, then there are also some very interesting connections to geometry, Calabi-Yau manifolds, and also to number theory, the so-called Gauss composition law, the approach by Bagova. And so these are like variations of the theme. It leads to connections to quantum information, geometry, and number theory. Then the second and the fourth paper are more on the technical aspects of complexity, for example, search and counting to decision reductions, as well as we want to make the reductions more efficient. So for this talk, we will focus on the first one, namely how tensor ISO captures isomorphism problem for several algebraic structures. And if you're interested in these 2 aspects, there's a recorded talk at IAS on some aspects of this. So we want to talk about some other algebraic isomorphism problems. So I kind of need to introduce to you, for example, this so-called group isomorphism. So the group isomorphism, which basically you are given 2 finite groups, you want to know whether they are isomorphic or not. So it has been studied in TCS and also computational group theory since the 1970s. And it's a very nice observation going back to Professor Tarjan. It's recorded in a paper by Miller. So that group iso, you can have a very natural n to the log n time algorithm because a group can be generated by at most log n many elements. And for group iso, actually, there are two versions or several versions. We only care about the so-called verbose version, where the Cayley tables are given, or the multiplication tables are given, and also this succinct version, namely we are given the so-called generators of matrix groups over finite fields. But basically, just remember there are two versions of group iso, the verbose and the succinct version. There are polynomial time algorithms known for different group classes, but these are not important for this talk. The important thing is that there exists some group class that resisted decades of experts called P groups of nilpotent class 2 and exponent P. So yeah, it's quite a mouthful. So we don't really want to go into the definitions here. But instead, I want to emphasize that if we look at this so-called bottleneck, one of the bottleneck classes for group isomorphism, actually, the structure of these groups is relatively simple. It's just determined by some so-called commutator map. And when you look at this commutator map, and then you build some correspondence between group iso and this multilinear algebra problem. It's called skew symmetric bilinear map isomorphism, where you have two vector spaces U and V over the finite field of order P. Then you have two so-called skew symmetric bilinear maps, F and G, and you want to know whether there exists invertible matrix A and invertible matrix B such that these two bilinear maps are the same up to the action of A and B. So pictorially, okay, so it's still, maybe too wordy, but when we want to record such a bilinear map in our algorithms, we essentially get a tensor. So if the vector space is fp to the n and the other vector space is fp to the m, what we get is just an n by m tensor recording the bilinear map. So that's the connection. Namely, we started with groups, but up to some minor group theory and not mild group theory, we have tensors underlying these groups. And to test the group isomorphism for this group class actually turns out to be something like a tensor isomorphism problem. That is, you have two tensors, both of the size n by m, and then you want to know whether there exists invertible matrix A doing the linear combinations of the horizontal slices, and the same A doing linear combinations of the vertical slices, and B doing linear combinations along the third direction. So this is starting from group iso, we reach to tensor iso, but some variation of tensor iso, right? Remember the original version of tensor iso, you have three matrices acting on the three directions. Here you only have two, A and B, where A acts on the first and the second directions. So this is a group iso, and then people also are interested in the so-called polynomial iso. So one version of the polynomial iso problem is the following. So suppose you have two quadratic polynomial systems or polynomial maps, and you want to know whether these two quadratic polynomial systems are the same up to invertible matrix A acting on the input and B doing the linear combinations on the other side. So I'll show you an example. So for example, maybe n equals to 2 and m equals to 3. So you have these three quadratic polynomials. And then the first invertible matrix A is basically doing linear combinations of these variables. So for example, x may be sent to 2x minus y, and y is sent to minus x. So that's what A is doing. A is doing linear combinations of the variables. And what this B is doing? B is doing linear combinations of these polynomials. For example, you can send the f1 to 2f2 plus f3, f2 sent to f1, and f3 sent to f1 plus f3. So, up to this linear combination of the variables and up to the linear combinations of these polynomials, of course, A and B will send this polynomial system to another polynomial system. And of course, for tensor isomorphism, for polynomial system isomorphism, you are just given these two systems of polynomials, and you want to know whether by linear combining the variables and linear combining the polynomials, you can transform one polynomial system to the other. So this is polynomial isomorphism problem. So these problems have been studied in cryptography since the 1996. And there are several variations, right? Here we're focusing on quadratic polynomial systems, but you can think of them, for example, we have A and B, but you can think of setting B to be identity. And there are also distinctions between homogeneous and inhomogeneous polynomials, as well as going to higher degrees. So it has been really intensively studied in crypto, but on the other hand, there seems no guidance regarding which cases are easy and which cases are hard. So this, this is problematic. If you don't have a complex theory as a guidance, sometimes you think some problem might be hard, but it has no relation to other hard problems. Maybe it can get broken after some time. For example, if you set B to be identity matrix, then actually there exists a polynomial time algorithm. But on the other hand, there does exist some polynomial complexity relation between, for example, the cubic form isomorphism. Cubic form are just homogeneous degree 3 polynomials. So, and the so-called algebra isomorphism. So this is established by Aguilar and Saxon. So now I'll quickly talk about the so-called algebra isomorphism. So algebra isomorphism, basically you have a finite dimensional vector space U over some field F. And again, you have some bilinear map, F and G, that is mapping U cross U to U. And you want to know, naturally, you want to know whether there exists the invertible matrix A doing linear combination on the U, but now A acts on the 3 sides, right? You want to know whether this A will change one bilinear map to the other bilinear map. So this is algebra isomorphism. Of course, when we talk about algebra, we will always think it's maybe, for example, commutative algebra or associative algebra or Lie algebra that then you need to satisfy the so-called Jacobi identity. But basically, this is the underlying structure. With further conditions, then you will get commutative algebra or associative algebra or Lie algebra. And this has also been studied by Grigoriev, Qiao Saxena, Aguilar Saxena, and Josh Groucho, and studied by several authors. So now, okay, so what we have done. So we have seen, we start with tensor iso, right? Then we also review some isomorphism problems for groups, polynomials, and algebras. They have been studied in different communities like DCS, computational group theory, crypto, and each of these structures, you can imagine, it has a very rich theory behind it, polynomials, right? Or the algebras, associative algebras, and so on. So now we essentially, the next thing is that we want to build relations between isomorphism problems for these, different varieties of algebraic structure. And that is the first main theorem. So all the problems we have talked about actually are TI complete, including the succinct group isomorphism with the so-called P group for class 1 exponent P, polynomial isomorphism, where we have quadratic polynomial systems or cubic forms, and also algebra isomorphism for associative or Lie algebras. So all these different algebraic structures, though they have come from different variations or different origins, but in different communities, they turn out to be polynomial time equivalent. So now we have, a kind of a better, more understanding of these isomorphism problems. First, it's very classical result that the verbose version of the group iso reduces to graph iso. Then graph iso reduces code equivalence and reduces to tensor iso. That's what we mentioned before. And then for tensor iso, we say that the group iso for this succinct P group iso, polynomial iso, and algebra iso, they are actually all polynomial time equivalent. So this is the first message, namely tensor iso can serve, hopefully, as a unifying problem for algebraic structure isomorphism problems. Any questions so far? Okay, so yeah, of course there will be some technical note. For example, this is subject to appropriate underlying field. When we talk about P group iso, it's over finite field of order P, and then for quadratic polynomial system, the field characteristic is not true. For cubic iso, the field characteristic should not be 2 or 3, but it's not very important, just 2. Okay. Okay, so we have seen the 3 tensor iso, right? 3 tensor iso seems capturing several algebraic structure isomorphism problems. But on the other hand, recall that matrix is a two tensor, right? A matrix is two tensor. To test whether two matrices are equivalent is in P by computing the rank. Then we say that we will see very soon, okay? Three tensor seems much harder. But on the other hand, it's also natural to consider four tensors, right? Or five tensors, or six tensors. For example, for four tensors, we are essentially given two four-way arrays with every number will have four indices. And then we want to know whether they are the same up to invertible matrices L, R, T acting on the first three indices and S acting on the fourth index. So it's very natural to consider these problems. And the question is, does it become harder when we go to four tensors or five tensors? And here is a theorem. The good thing is that we don't need to go to too much. Basically, everything reduces to 3. That is, D tensor iso Pauling time reduces to 3 tensor iso. So that's another result. This is more like 2 set is in P, but D set reduces to 3 set, which is NP complete. So, yeah. Okay, yeah, I got a lot of questions like this. So the reduction basically since if you have D tensor and the underlying vector spaces are of dimension n, it sends Fn tensor D times to Fn to the D tensor 3 times. So it's polynomial time because it's basically cube. The input size is cubed. Okay, so that's the complexity side so far. Any question or so far so good? Okay, now let's look at algorithms. And I assume hopefully now you are interested in how these problems will play out and whether it's difficult or not. So it'll be very instructive to compare tensor iso with graph iso. For graph iso, we'll be considering graphs with n vertices. And for tensor iso, for convenience, we'll consider n by n tensor over FQ, finite field order Q. Yep.
Very algebraic, but still consider.
We don't know. Yeah, it's a very good question. We haven't really thought about it. By approximate, you mean something like their. Okay. I think people in graph iso, I think there's a paper by Ryan O'Donnell and Yuan Zhou. They have considered this approximate version, but we haven't really thought about it. So far, tensor iso seems not very much studied. There are a lot of open.
Time against algebra.
Mm-hmm. Yeah, of course. Yeah, I agree. Okay, so maybe I'll keep going with comparing graph iso versus tensor iso. For first, the baseline, right? The brute force. For graph iso, the brute force is n factorial, enumerating all the permutations. For tensor iso, is q to the n squared, enumerating n by n matrices, for example. So the worst case, of course, we know this breakthrough result by Lassi-Babai from 7 or 8 years ago. It runs in its coarser polynomial time. It runs in time n to the log n squared. And for tensor iso, there was also for me, very exciting progress. That is, we can bring down from, on the exponent, bring down from n squared to O tilde n to the 1.5. So this is, I'll say a few more words after that, but this is the current best data. For average case algorithms, for average case basically means that suppose you have some random graph from Erdős-Rényi model, for example, then you want to test the isomorphism of this random graph with an arbitrary graph. So that's the setting of average case for graph iso. So for tensor iso, of course, you can also draw your n by n tensor every entry uniformly from FQ, right? That's a natural random model for tensors. So then we have average case setting, and for graph iso, it's quite easy in the sense that it's kind of linear time, O(n) squared. And for tensor iso, for the average case, we can do something like q to the O(n). So on the exponent, it goes down from n squared to n to the 1.5 to n, linear in n, but still exponential. Practical algorithm is even kind of more interesting because for practical algorithms, since the 1980s, people have implemented some software for graph iso, which is basically very efficient on most of the graphs, almost all the graphs you met in practice. This graph ISO software called Naughty, or there are several versions by different developers. So they can deal with graphs with 1 million vertices without problem in general. There, the game is that you are trying to come up with a graph that is hard for the software. So that's the game there. On the other hand, motivated by the crypto, as I will talk about later, we are also interested in practical or heuristic algorithms. And what we can do now is something like Q to the half n. This half n is actually very important because, for example, this big O is hiding something like 5. If you have something 5 times n, then n is 4 or 5, then it's already not practical at all. But on the other hand, this Q to the half n means that when n is even 20, and Q is small, for example, sometimes you can do something, or n being 10, for example. So basically, if n equals 20 and Q equals 11, you do not expect this algorithm to run fast. But when n is 10, for example, this algorithm will be okay. But on the other hand, it depends on heuristic analysis. So we don't know, we don't have a rigorous bound on the running time. For graph ISO, yeah, exactly. You can tell, right? But on the other hand, you basically there the game is that you can easily, even from the degree sequence, you can already tell some difference. That's a very good question. I'm going to talk about it because it's also related to crypto. So we don't even know one easy to compute and useful in there. Okay. So yeah, I'll say a very few words about this worst case algorithm. So we can test tensor ISO in the worst case in time q to the n to the 1.5. And I should really add that the first breakthrough was done by Qiao Sun, and who devised this q to the n to the 1.8. So our algorithm basically improved from 1.8 to 1.5. But the first breakthrough was by Qiao. And then, because we have seen the relations between tensor ISO and group ISO and so on. For group ISO, for this so-called bottleneck case of group ISO, we can now have an algorithm running in time n to the square root log n. So remember, the bottleneck has been there, namely this n to the log n time algorithm, the naive generator-based algorithm runs in time n to the log n. For a very long time, we want to know whether this log n can be improved. Now it can be improved first by Qiao from log n to the 5/6, then now from 5/6 to 1/2. So that's the worst case. So I think it's very exciting, very nice. But on the other hand, our current technique seems to be somehow stuck at n to the 1.5. So it's unclear whether we can make it better. So that's the tensor ISO algorithm side. Questions? Okay, so now we can go to crypto, right? So hopefully now you are more or less convinced that tensor ISO should be a hard problem in general, at least for now, right? So if we have some hard problem, let's see if we can use it to do something. And so this goes back to the setting of the question. It's a pretty classical old question that is, can graph ISO be used in cryptography? So this question was pondered in the 1980s, 1990s by Brossard and Crippier, Griffiths and Young around that time. And but on the other hand, based on what we know about the algorithmic status of graph ISO, it seems unlikely, not just because of Babai's algorithm from a few years ago, but also because of very practical and fast software for graph ISO, the heuristic ones. Even those heuristic algorithms are already implemented since the 1980s. But on the other hand, are there useful invariants in isomorphism problems in cryptography? This is something probably people didn't really phrase it much in this setting, but actually yes, because discrete logarithm is actually can be formulated as a morphism problem. So this leads us to the so-called group action framework for cryptography. That is, suppose we have a group G acting on a set S. And we have also a group action, suppose F is our group action. And then we need to assume, for example, the group operations, the action F, and the sampling from G and S, they are efficient. We'll make some mild assumptions. And then once we are given this group action, a natural problem associated with the group action is the so-called orbit problem. That is, we are given two set elements in the set S. Are they in the same orbit? They in the same orbit mean that there is some group element G that transport S to T. So that is the orbit problem in the group action framework. And more useful in cryptography will be the search version of this orbit problem. That is, we are given S and T in the same orbit. So we know that they are isomorphic already. Now the question is, can we find the group element G that transport S to T? So this is the group action framework. And for example, the discrete logarithm can be formulated into this group action framework, where the underlying set is actually a cyclic group of order P. You exclude the identity element. And the group G will be the automorphism group of this cyclic group, which is isomorphic to ZP, the multiplicity group of ZP. And then the question is, given G and H in S, we want to know whether there exists A. Now A is just some element in ZP, such that G to the A equals H. So basically raising powers, right? Now you see that it's basically logarithm. So this is to find this A will be the logarithm question. So this is discrete logarithm putting in this group action framework. Also, graph isomorphism can also be put into this framework. That is, S will be the set of subsets of n choose 2, where n choose 2 is a set of size 2 subsets. So essentially, this is like all the graphs on the vertex at n. And then G will be, the symmetric group on the set n, which is permuting the vertices. So graph iso then can be formulated in group action framework by saying that we are given E and F in S. E and F are essentially the edge sets. We want to know whether there exists some permutation of the vertices that send these two edge sets from one to the other. So this is also graph iso, but putting into, just reformulating it in a group action framework. Then tensor iso is also, you can formulate it easily because S now is a set of bilinear forms, right? From U vector spaces U cross V cross W to a field element F. Then the group here will be GLU, the general linear group on U, general linear group on V, and general linear group on W. So essentially, tensor iso is also a orbit problem for this set S and this group G. Okay, so now we have formulated something useful in crypto in this group action framework, something not very useful in group action framework, and now the question is tensor iso, right? So for group iso, for this group action framework, then there's a pioneering work by Brass and Young in the 1990s who defined the following. They define a group action F is a one-way group action if for some set element little s in S, you define a function F depending on the set element S by sending a group element G to the application of this group element G to this set element S. So if this is a one-way function, you say that this group action is a one-way group action. And basically, one-way group action is assuming that the search version of the orbit problem is hard. Because at the end of the day, you know this S, which determines this orbit. Then you know some other set element T in this orbit. Your question is to find the group element transporting S to T. And then there's also a so-called pseudo-random group action notion, which corresponds to so-called decision notice-Hellman. So what is a pseudo-random group action? This also relates to the question of Mark. That is, suppose we have a group acting on a set, G acting on a set S. Then we define two distributions, right? The first one is a so-called random distribution, where S and T are just random set elements. Then you have the pseudo-random distribution, where you have S and T, where S is a random set element, and the T is actually random sampled from the orbit of S. So here you see that in the first random distribution, S and T, if your group action is intransitive or something, then S and T are highly likely S and T are not in the same orbit. But here in the pseudo-random distribution, S and T are guaranteed to be in the same orbit. So this is the random. Then of course the group action is pseudo-random if no polytime algorithm can distinguish these distributions. And you can use this pseudo-random group action to basically recover the so-called decisional Diffie-Hellman, where the set element set will be pairs of group elements. Cp the cyclic group of order P, and the group will be the automorphism group of Cp. Then this action of G on S will be basically sending a pair of elements to raise it to the power. For this A, inside alt Cp, you raise to G to the A and H to the A. So that's the action. Then if you look at the random distribution, remember S and T are from S, but now this capital S is a pair of elements, right? So S and T will become G1, H1, G2, H2, but because this is a transitive group, so you can write H1, H1, G2, and H2 into G1 to the A, G1 to the B, G1 to the C. So this is what you usually see, right, in the decisional Diffie-Hellman. And then for the pseudo-random distribution, of course, you have the first element being G1, G1 to the A. You have the second element being S to the B, which will give you G1 to the B, G1 to the AB. So you get G1, G1 to the A, G1 to the B, G1 to the AB. So this is basically just to show you that the pseudo-random group action basically covers Diffie-Hellman in a natural way. Okay. So having introduced the assumptions, namely the group action could be one-way or pseudo-random, then you can build crypto applications by assuming that you have some one-way or pseudo-random group action. The crypto applications include bit commitment, digital signature, which is very important because digital signature, for example, is based on the so-called Goldreich-Mikhaili-Riggerson, this zero-knowledge protocol for graph ISO. And then you use the fiat Shamir to transform this interactive protocol into a non-interactive one using hash functions. And very recently, there is also a very interesting paper by Morime and Yamakawa. So they show that you can also do public key encryption, but there is a quantum public key encryption, namely the ciphertext will be a quantum state. So you can do various things, assuming that you have one-way or pseudo-random group actions. But then the big question is, right, do we have any candidate group action for one-way and pseudo-random? That's basically where the tensor ISO comes into the picture. For example, discrete log group action, right? It's one way for classical, but it's not one way for quantum because of Shor's algorithm. Then graph group action is not one way for classical because of Babai's algorithm or the practical software. But there is a very interesting result from quantum algorithm, namely the so-called standard techniques from Shor's algorithms does not work. This is a result by Hallgren, Moore, Rotella, Russell, and Sen. So the basic idea is that you need to do some Fourier transform and look at the irreducible representations. But then for symmetric groups and general linear groups, the symmetric group representations are of large dimension. So that's, of course, it's oversimplifying, but that's one kind of the reason. So then Moore, Russell, and Verrani, they say that this is kind of like the strongest such evidence we have about the limits of quantum mechanics. So this is very interesting, right? Why is one way for classical but not quantum? Why is not one way for classical, but somehow there is some evidence for quantum techniques not working very well there. So tensor ISO seems to be in a kind of like the sweet spot, which seems to be difficult in practice from the algorithm we talked about before. And it also inherits the resistance to the so-called quantum standard techniques. So that's why tensor ISO seems to be useful and interesting for this as a candidate for one-way or pseudo-random. So I want to talk a little bit about this. Is also related to Mark's question. That is, for tensor ISO to be pseudo-random, we basically need to distinguish between the following two distributions. The random distribution will be you have two random n by n by n tensors, A and B over GFQ, finite field of order Q. Then you have pseudo-random distribution where you sample a n by n tensor A. Then you basically sample three invertible matrices and apply these three invertible matrices to this A, get your B, get your another tensor B from the same orbit of A. So now I give you these two, and can you distinguish, whether it's random or pseudo-random? And yes, if we have some so-called isomorphic invariant, this isomorphism invariant should be useful in the sense that first is efficiently computable, second is distinguishing enough. Namely, two random tensors should have different values. For example, tensor rank, right? Tensor rank is apparently a isomorphic invariant. At first, tensor rank seems to be hard to compute in general. It's NP hard, right? So in the general case, so it's not efficiently computable. And if you sample two random tensors, then they are with high probability of the highest tensor rank. So it's not that useful either. So it's not that distinguishing either. So that's the funny thing. We don't know any easy to compute useful isomorphic invariant for tensor iso so far. There are also even some support evidence from the invariant theory. So many of the TI, so-called TI complete problems are also eligible. I don't know, cubic form isomorphism or this P group isomorphism. So I'm basically to the end, so I think I'm on time. I'll just quickly mention to you one nice thing. So we start with complexity, right? Then we go to algorithms, then we go to crypto. I want to somehow go back a little bit. So namely, we have been working on this crypto, tensor iso-based crypto for some time, tensor iso-based crypto for some time. And one desirable feature of the digital signature schemes is to have the so-called quantum random oracle model security. I assume that some of you probably know this model much better than I do. And but for group action framework, a digital signature design based on the Goldreich, Macaulay, Riggerson, and Fiat-Shamir, it has the QROM security if the stabilizer of a random group of a random set element is trivial. So then this leads us to ask, if you are given a random tensor, and is the automorphism group, namely the LRT, making it stabilized or making it the same, is it trivial or not? So it turns out it's a very interesting problem, and we spent some time on it. And then in the paper, joint paper with Marcus Blaser, Inani, and Alex Rogovsky, we show that when n is large enough, a random n by n tensor does have the trivial stabilizer. So which is nice, right? So it somehow shows there's a QROM security for our digital signature scheme. But it also has some interesting consequence. That is, we could improve the estimation on the number of isomorphism classes of P group or class 2 and equivalent P, which was estimated by Higman in the 1960s. And because of all the relations between tensors and this class of groups and so on, we can also improve the estimation on the number of isomorphism classes. So yes, so basically that's all I want to tell you. That is, we start with tensor isomorphism problem. Then from the complexity side, we see that tensor isomorphism is like polynomial equivalent to many other isomorphism problems of algebra structures like groups, polynomials, and algebras. Then from the algorithm side, we see exciting progress in past few years, but it's still exponential, which support us to use it in cryptography. And we see this pseudo-random group action and whether we have nice isomorphic invariant for tensor iso and so on. So there are still a host of questions over there. And I guess then that's all I want to tell you about. Thank you so much. Questions, please. Yeah, Yasin. It got all the work. Yes, we have digital signatures, but so far it's still kind of limited to the mini crypt. For example, if you look at the applications, bit commitment, digital signatures are definitely this is very classical. But for the public key encryption or key exchange, we don't get it in general because, for example, key exchange requires commutativity. But here, tensor iso is based on very non-commutative group, so we don't have that automatically. But even for this public key encryption, so far the ciphertext is also quantum. So we don't know whether could be a classical, for example, classical ciphertext public key encryption. So we are still trying to expand the crypto functionalities. Yes, so far, for example, if you just assume pseudo-random group action, you are not really looking at the underlying object structure, right? You just have this group action and you're seeing the pseudo-random and do things. If we just limit ourselves to this pseudo-random property, then exchange, for example, will meet the difficulty of non-commutativity. Because if you have, actually I should probably could mention that there is also a one-way or pseudo-random group action from isogeny-based crypto, where they look at the so-called class group action on elliptic curves. There, they are proposing this as a pseudo-random group action candidate, which is commutative, so you can still have Diffie-Hellman exchanges. But for tensor ISO, because the underlying group is highly non-commutative, so we don't quite know how to do exchange.
Thank you.